Thank you very much. It's so wonderful to be back at IPAM. Too many projects have started already in the last few days. This is a very generic title, and that was given months ago, and I'm going to sort of focus down into to essentially force field, making force fields, and I've omitted a few things that Matthias and Michele in particular have talked about already. So, because of the diversity of your expertises, I thought it is worth spending a few slides just introducing what this task is that we're trying to do. So when we model materials, there's a vast length scales and time scales that we need to capture, and materials modelers use a hierarchy of models to do that. So all the way from treating a few atoms down to essentially treating continuum systems and time scales. We can investigate things that happen basically instantaneously, all the way to aging of concrete, which then happens on the time scales of years. And there are models for all of these systems, and I'm mostly interested in this lower end, where we have models that are very, very accurate, and their capabilities are rather limited. And these timescales and capabilities, accuracies, are sort of rather provocative, but it's a log scale, so I don't have to update them very much, and they really don't get a lot of criticism. At the very bottom, we have quantum mechanics, and people rarely talk about it, but it is, when I talk to people who work up here, it's sort of an amazing thing that quantum mechanics, unless you have really high energies, cosmological models, it's not really an empirical model, right? We're not fitting anything. It's the real thing. And that's sort of unusual in broadly speaking in science. So we know the Hamiltonian exactly. We know that this is the equation we have to solve, except that that's really, really hard, right? So for every position of every atom, the wave function is an object which has as many dimensions as atoms you have. It's an unknown n-dimensional function, and it's unique for each nuclear configuration. So that's really hard. But there are approximate ways of solving it, and the approximations are decent enough for most of chemistry. On the other side, and this I sort of whizzed through, there is empirical modeling, and let's not discuss that anymore. But in the middle, there is an interesting place, because if I have the 3n positions of n atoms, and someone has solved some approximate version of the Schrodinger equation for me, then I get an energy out of that. Let's call that a potential energy of the atoms. And now there are no longer any wave functions, and this is a 3n-dimensional function, a single one, as a function of the atomic positions. And if I knew that, if I had a good, fast surrogate for that, I'd love to do it exactly with quantum mechanics, but I can't, it's too slow. If I knew that function, I could apply Newton's law to move the atoms where they want to go. And that means molecular dynamics. It means that I can discover the structure of materials, investigate their stability and their transformations. And 99% of chemistry and material science is that. And if we look at where this lies in this hierarchy, it's sort of here. So I have explicit treatment of electrons to the left, and no electrons, only atoms to the right. And that's exactly where the jump is in the capability in terms of treating numbers of atoms and in terms of timescale. So this is where we are hoping to inject machine learning. So that's the niche. People, of course, have been doing this kind of function fitting before, and there are three main areas of science where these that are called force fields or potentials that are extensively used. And in organic force fields, transferability is key. So people define very simple models of just pair potentials, to pair interaction between a pair of atoms, maybe an interaction of the angle, and if you're fancy, then you also have a dihedral term that's a four-body interaction, and these can be parameterized quite accurately for very small displacements away from your reference structure. And typically, these don't allow reactions, these models, so you can't break any bonds, and you fit them empirically to macroscopic data. And because you do that, it's not actually a very good fit to the underlying quantum mechanics. So this is a typical plot. So here's some reference quantum mechanical energies. These are some predicted energies of one of these models, and this is for a hydrocarbon, and this will be the perfect prediction. And you have errors that are on the order of sort of half an eV, and if you express that in temperature, that's sort of 6,000 degrees. So that's the energy of an atom in a material at 6,000 degrees, but that's really high, and we're not interested in this material at 6,000 degrees. We're interested in these kinds of materials at 300 degrees. So the temperature that's relevant, the energies of the atoms are really, really very small, and the errors are many orders of magnitude larger than the energies we're actually interested in. That's what I mean by a bad fit. Then there are material models. So imagine a crystal like this. This is a diamond, and we're interested in creating defects, creating surfaces, the formation of such structures. So there are models that are reactive, so they need to break these bonds. They're even less accurate than these organic force fields. They're based on very simple ideas about the bonding in materials. Here's an example. You take an approximate, very simple approximation of the electron density around an atom, and you add up all the contributions from all the other atoms, and you plug it through a simple nonlinear function. And when you do that, for example, here's a silicon model. These are observables that you want to predict. These are different models. Some of them are of this type, and these are fractional errors with respect to the quantum target in all these properties. And you get these errors generally 20, 30, 40, 50% error, which essentially means that you can, if you use those models to do science, you can get trends, you can understand basic driving mechanisms, but no detail, and certainly not quantitative. There's another area, which is small molecule gas phase chemistry. So here, you're interested in one or two very small molecules, like here's a pair of waters, and typically, the typical task is to predict this potential energy so accurately that the vibrational modes, the vibrations of these atoms, and the light that absorbs or gives off is predicted with respect to experiment, and that is successful. So for these very small systems, there are a whole bunch of methods that typically they rely on systematic expansions of this potential. Essentially, think of it as a Taylor expansion, except there's a bit of symmetrization going on. And the number of variables is then the number of atoms, and all of these methods scale sort of exponentially badly because it's a systematic polynomial expansion in these coordinates. They are extremely accurate, and nobody has done them for more than 10 atoms. And they don't scale, and they're not extensive, and so on. So the whole goal of our entry into this field 10 years ago is to have this kind of accuracy with this kind of reactivity and flexibility and this kind of transferability. And that's essentially the sort of overarching goal. And doing molecular dynamics is actually important in the sense that lots of people spend lots of money doing it. So this is one of the largest civilian computers in the US. This is from the 2017 report, and this is these are all the highest usage codes, and this is on a log scale. So this is 1 giga units, 100 million, 10 million, and then the expansion into this is the lowest part. And I've colored the different bars. These are codes, and by looking at the names of the codes that are being used, I can tell what kind of tasks they are performing. And all the red ones are essentially doing these kind of force field simulations. So no electrons, but molecular dynamics. And then the green stuff is doing electronic structure, approximate quantum mechanics. And you can see that the sum of all the green is probably less than this fourth ranking interatomic potential. This is the equivalent plot from the UK. It's actually the reverse. It's a much smaller system and slightly older data. And you can see that almost half of the total amount of usage is taken up by these two tasks. So either interatomic potential, force field simulations, or explicit solving of the Schrodinger equation. In the UK, due to historical reasons, the expertise of the groups and the kind of science that people are good at, there's a reverse. So the majority is actually electronic structure, and the minority are the force field simulations. So if we're going to try and use machine learning to make better force field models, it helps to ask whether this is actually possible. So quantum mechanics is a long-range theory, and if you're going to fit something in a moderate number of dimensions, 10, 20, 100 perhaps, so that sounds reasonable, and have it be then linear scaling and extensive, then we need to separate long and short-range interactions. So there are sort of three ways. These are the long-range interactions: polarizable electrostatics, van der Waals dispersion, perhaps charge transfer. And there are essentially three strategies. So either you pick a system where you can ignore them. That's an extremely successful strategy. And that's what almost everyone, including myself, have been doing. And then if you don't want to do that, and this will come back as when I talk about challenges, if you know the analytical form of these interactions, so Coulomb interactions essentially with some where you know the source terms, then you can subtract them before you fit the data and then add them back when you predict. And if you don't know the analytical form, or you think they're not good enough, then you can try and also learn those or fit those, and that's really hard. And essentially very little progress has been made into that, although some have done that. One of these, it would be nice to test how these approaches work before we do any machine learning. And a great system for testing this, and this for what I have data to show for you to explain how these tests are done, is amorphous carbon. There are no electrostatics, so it's not a terribly long-range interactions in this system, but nevertheless, when you have these low-density systems, low-density amorphous systems, it turns out, you will see on the next slide, that interactions are much longer ranged than when you have these high-density, almost diamond-like, but still a bit randomized systems. So how do we do the locality test? You take a system, it's just a cartoon illustration, you pick an atom, and you define a sphere around it where you fix the atoms. And then then you create a replica of all those of all the systems where inside the sphere everything is the same, and outside, using some procedure, you randomize the atoms. And then we push that through our favorite quantum mechanical simulator and get a force on that central atom. That's the derivative of the energy with respect to the atomic position. We take those set of forces and we compute that. We look at their standard deviation. And then we plot this as a function of the radius of the sphere. So if the interactions are local, then as long as my sphere is big enough, then the forces should only depend on what's inside the sphere, and this standard deviation should be really small. If the interactions are very long-ranged, then no matter, or as long as I bring this sphere radius out to larger, I will still find variation as in this force, because there are things further away varying that affect it. So here's this plot, so the plot of the variance as a function of the fixed radius for diamond. So I take the diamond crystal and I distort the atoms a little bit, and you can see that the force variation really goes down and basically is zero after about half a nanometer. If you look at graphite, which is the two-dimensional form of carbon, then you get a little bit of reduction, and then it basically plateaus. And you need to go much, much, much further, essentially so much further that we can't even reasonably compute it to get this force down. And this almost 1 eV per angstrom is sort of an enormous force. That's the typical force that you deal with when you do these simulations. So, and here's the amorphous carbon data. So if you do random distortions, both of them go down, but not so great. These are two different densities. But if I take MD-induced distortion, so this is a sampling which is much more realistic to what you're going to encounter, then for the high-density, diamond-like situation, you get a nice reduction, and again, at about half a nanometer, you're basically done. And for amorphous carbon at 2 grams, it's not as bad as graphite. It goes down, and at 7 angstroms, so almost a nanometer, you still have substantial forces. So this is a test, and we didn't have to do any fitting. But we are finding out whether the thing that we want to do, the fitting that we want to do, is actually fittable. So it gives a limit of force field accuracy for a given cutoff. I can turn it around and say, if I give you the cutoff, what force accuracy is actually achievable given infinite data and perfect fitting? Because if the forces aren't actually determined by the environment within the cutoff, of course, no fitting mechanism will get them right. So with that introduction, I would like to return to this decade-old promise, or pose this as a decade-old promise, Jörg Behler's paper from 2007 and ours with Rishi in 2010. And we said, okay, we're going to do this with machine learning. Neural networks here, Gaussian process, kernel ridge regression here. And my message for 2020 is rather provocative. I'm going to claim that this problem is solved. Not just by my group, but by a few people in this community. That the short-range quantum mechanical regression problem, the force field problem, has been solved satisfactorily. And I'm very happy to be challenged on this and modify and refine this claim, but that's the essence. I hope the next 30 minutes that I will sort of demonstrate this. And of course, there will be things that can still be improved and optimized, but we are doing new kinds of material science with these solutions, with the models that we built. So then I won't talk about regression because very many of you are really experts in that and how neural networks and Gaussian processes, kernel ridge regression works. Let's take that as read. But representation is interesting. There has been some talk about it earlier. So here's just a 1 or 2 slide refresher. So I like these density-based representations of atomic structures. So you put a little Gaussian kernel or any kind of convolution kernel on the atoms around atom I with a finite cutoff and some cutoff function that takes this density smoothly to 0. And by doing this, this density that you've built is permutationally invariant, smooth, and continuous. But it's not rotationally invariant. And in order to make it so, you project it onto a basis. And one way to do that is to go into the spherical harmonics basis with some orthogonal radial basis set that you're free to choose. And given these coefficients, C and Lm, if you sum them over M, C dagger C and Lm, C n prime Lm, we call it the power spectrum, P and n prime L. It's a 3 index array. And this is rotationally invariant. And essentially, what we've understood through this work about 6 years ago is that the dot product of this power spectrum array of 2 different configurations is equivalent to the integrated overlap of these densities. So you take these densities around 2 atoms, you integrate them, you multiply them, integrate them, square them, and then you integrate over all possible rotations of one of the densities. That's the r hat here, and that rotationally and spatially integrated overlap is the dot product of the p's, and we use that as a kernel. If you just do it it's a scalar product. So if you just use it linearly, then you can use it in linear regression. If you raise it to some small power, then you can use it in a kernel method. And as has been mentioned before, particularly by Matthias, because of this square here, this is essentially equivalent to 2 and 3 body description, knowing all the angles and all the distances within the cutoff radius, but in a nice and smooth and permutationally invariant way. In what we've learned much more recently is that this p vector, SOAP vector, really is, we call it SOAP, smooth overlap of atomic positions, and it really is a projection onto basis functions of this density. And in Cheriotis-Michele's notation, you take this environment, which we represent with the density. The 2 here represents the squaring of the density in that integral, and we have chosen to project it onto this spherical harmonic basis. But it turns out that everybody's representations are actually the same, are actually projections of this density. So Jörg Behler's symmetry functions, MBTR from Matthias, Anatole's histograms, even Stefan Mala's scattering transforms, and even a bispectrum that is in SNAP from the Sandia people are actually all density projections with some choice of basis and some choice of the convolution kernel. And of course, this throws up the question of what's the best basis to project onto. And I like mine, but it's not the best, I'm sure. So that's going to be very interesting in the next few years. I like the YLMs, which still gives you, of course, a lot of choice in the radial basis for many reasons. There's a very natural extension to expanding non-scalar properties, and Michele has talked about this. So the same kernel that we build for scalar properties, if you insert the Wigner matrix into that double integral, then this becomes a matrix kernel, and depending on that lambda of the order of the Wigner matrix, this is a suitable kernel for regressing vectors, second rank, rank lambda tensors, essentially. The YLMs also, as pointed out by Ralph Draughts very recently, allow you to create more invariants. So it's not only the C dagger C that's an invariant, but I can have 3 C's, and I've inserted this sort of what is called the Wigner 3J symbol here, or I think this is a 6J symbol, and that's a set of coefficients, and it's guaranteed that this summed over all of these indices, is actually a rotational invariant also. And this goes on. So you can have an arbitrary number of product of these YLM coefficients with suitable prefactors that can be recursively and efficiently computed, and this gives you a very, very rich set of invariants. And Ralph says, why don't we do linear fitting rather than kernel fitting or neural network fitting in just a second order invariance? We can take the whole series and do linear fitting, and he has shown some baby example where that was quite successful. Yes.
In this equation, the C is that the number of these terms that corresponding to the interaction order?
Yes. You will get, each C will bring you an extra neighbor. So that's, but the cost of evaluating these, no, it does not scale badly with the number of neighbors, and this has been shown by Alex Shapiev and also Ralph, that there is a resummation that you can do. That's, I don't have it at my fingertips. I couldn't show it to you on the board. But essentially, it's okay. It can be computed for small cost. These are these invariants themselves. You don't need to sum over every triplet, every quadruplet, every quintuplet. Okay. So another very nice thing about these YLMs, which I like a lot, is, of course, I've been talking about atomic environments so far because I want to create force fields, but there are many, many other tasks to be done with atoms, and often you want to describe entire molecules or entire periodic systems. And here's a cute thing that you can do. Take these C coefficients and average them over all atoms in a molecule. No need for any cutoff. Or if you have a periodic cell, make your cutoff bigger than the periodicity, and then average these C's and just do the C dagger C, or in fact any of these higher order ones, to get an invariant, now a single one for the entire structure. And that's a single invariant that describes everything, and you can then regress properties of the entire structure using these quantities. And there are other ways to construct structure kernels. Again, here's a paper, again, instigated by Michele Ceriotti. Here's sort of a matrix view of some of the methods that are using some of this technology that I've explained. And these particular ones I've highlighted because they're all in lamps. So these are actually methods, I call them methods, but really these are schemes, right? Everybody choosing all their parameters and everything, every choice is made. There's ours, sort of SOAP gap from my group, the SNAP I mentioned from Sandia, Baylor-Parnello neural networks, Jörg Baylor. MTP I haven't really talked about. It's a polynomial expansion, again, rotationally and permutationally symmetric, and this is sort of Ralph's. And what you can see is that if I can choose how I make the density, we smooth it with a Gaussian, others don't. We can have basis sets. Ours is complete in that we take the entire NN'(L) array. So does SNAP. Jörg chooses them in some way which is pretty cryptic. MTP, but it's very fast because he chooses just a few. MTP, again, Alex Shapiev goes down into sort of alpha mode and chooses a few of the invariants and achieves very, very fast models. Ralph Draughts would say take all of them. This leads to certain dimensionalities. Other people use different kind of regularizers or not. And the regression, again, people pick their favorite stuff. And now we can play. There isn't quite software that allows you to make any choice, but I'm sure that won't be for so long until we have software where you can make any choice that you like. So I have a few slides on benchmarking because these are recent papers that have come out in which some of these methods are tested. Again, not with arbitrary choices, just with each developer doing their own. And this is an image, I think something similar was shown by Matthias. So this is these are the metal alloys, binary alloys. The work is from Gus Hart's group. We fit to these FCC configurations with the two different atoms being, with each atom picking one of the two of these alloy components. And what you see is that broadly, all of these methods are broadly comparable. The largest difference is sort of a factor of 2. And we've ordered here the alloys in order of accuracy, and the different alloys. Some alloys are really much harder than others, but the gray bars show you the relative error. Okay, so niobium nickel is not actually hard in terms of fitting. It's just that all the energies are larger. There's a bigger misfit between them, and the fractional error is really the same. And we sort of get 1%. Essentially, these are now percents for the fractional, and we get 1% error, which is really rather good. This is from another paper where these methods are being compared on now not on lattice, but for molecular dynamics benchmark tests. And we have errors as a function of number of training structures, and then we have the energy errors, the distribution of the energy errors for the largest training structures. And what you see is that GAP and MTP are very accurate, but the others aren't far behind. And this is another sort of heat map, the different methods and the different materials, and it's energy and force errors. And what you see is that this is what I mean by the problem is solved. These errors are really, really rather good compared to what we had before. So the empirical force fields, after decades of development, aren't good enough, and these methods are. We can do the science that we want with them. Yeah?
What data you use here?
MD. So this particular, that's always, so these are the first few benchmark papers, and this is
not the testing in the training
it's MD it's MD data. That's a big problem. I'll come to that in a moment. How the databases are constructed. They're rather ad hoc at the moment. And when you have all these developers bring 2 authors, you have a 10-author paper, plus the 2 who are unbiased, they are running the tests, and we all have a big fight about what kind of data you need and how much, because the neural network guy says, no, give me 10 times more data. And we all say, well, go away. We don't need 10 times more data. That's your problem, not ours. Right? So this is the problem of benchmarking, but it has to be done, and these fights have to happen. Yeah?
You show the accuracy, and I would agree with that, but the flip side is, of course, that they are several orders of magnitude faster. So how about that part?
Just wait. Okay, that's your plot, right? Sure. So MTP is very, very fast. It's based on polynomials, and Alex Shapiev. This is partly sociology, right? Alex entered this field in 2017, and so how is he going to make an impact? He set out to say, okay, I'm going to take speed really seriously, because we already had these kinds of accuracies. So he put in a huge amount of really good effort into making that potential fast, and we didn't. And hold my hand up. We spend doing other things, and we are 100 times slower at the moment. But you mentioned yourself that, I think it was you, you change the radial basis and there's a factor of 10. And that's sort of coming slowly.
Oh, I was referring also to the force fields, right? Because these are...
Oh, yes. Yeah, sure.
Accuracy, but the force fields are a lot faster.
Well, the force fields are 1,000 times faster than gap, but that's sort of here. Okay. And the question is not that far, right? Once you take this Pareto front. And we're talking about force fields that are seriously usable, not Leonard-Jones. Okay, so here's what's wrong with MTP. Here's what's wrong with polynomials. So here's a test where we take again the FCC data set, but now it's not fitted to MD. We fit just precisely to the different FCC configurations. They are actively learned. So we pick the ones that are, actually Alex Shapiev picks them, that are somehow out of scope until we've had enough. And then we test. And it looks good. So we test on a liquid. So that's a pretty amazing test where you fit only on perfect lattice configurations of a binary alloy, and then you run it at high temperature. And again, so I know these numbers don't, you need to believe me that when we have a force error, a median force error that's sort of 0.1 eV per angstrom, that's close to the locality limit. So that's close to the best possible force error that you can get. So these are pretty good. Phonon spectra is the vibrational mode, energies of vibrational modes, and there are three curves here, the quantum benchmark, and then gap and MTP, so the SOAP-based model and the polynomial model, and the fact that you see the mole overlap is pretty good. But extrapolation is a problem. So let's take two of these configurations, this one and this one. There, you don't see them directly, they're rotated, that they're both FCC. So this one and that one are just different ways of creating a perfect on-lattice structure, and then we move linearly between them. And we've constructed that paths in such a way that the atoms don't cross each other. It's not a minimum energy path, but it's a reasonable transformation path. And what you see when you do the quantum evaluation is that the energy, of course, goes up and comes down again. When you evaluate this with the SOAP-based model, the energy goes up and comes down again, and the error is not insignificant, a factor of 2. This is a log scale. So on the energy. The polynomial potential goes down and up again, and this is a log scale. This is 10 to the minus 3. So that's 1,000 EVs. This is a hole in the potential, and you will find it if you run MD on a crystal. Eventually, it'll kind of fall into that. And that's what polynomials do when you go out of scope, and that's what smooth descriptor-based kernel methods don't do when you go out of scope.
So what is the difference? Sorry.
Yeah, no. So MTP is a up to 20-degree polynomials in the Ri.Rj, right? And it's and regularization is a nightmare, and it's hardly done because. And gap is a kernel ridge regression model on the SOAP density-based representation that I showed you. Okay, so but it's much more expensive, right? So here MTP is 100 times faster. But you get to the crazy place 100 times faster, probably, right? Okay, so MTP can be used and is being used to do new science as long as you manage to avoid those situations. Okay, so I suggested that this problem is solved, and what I want to, my evidence for that is it's good enough, it can be still improved, but it's good enough to do new science, and I'm going to show you a few examples, but we've done a lot. So these are papers from 2018, mostly done by Volker Deringer, who's now professor in Oxford, and we've done, for example, carbon, deposition of a carbon film, 10,000 atoms thrown one by one. We see how a carbon film grows, and this was done before, but not correctly. The resulting structures didn't match experiment. And when you do it with the potential that we make, you get structures that match experiment in every possible way that you can measure, and you discover new mechanisms of how this carbon manages to not graphitize. So typically amorphous carbons, if you hit them hard, they go into useless graphite, useless from a mechanical point of view, and these are hard coatings that stay sort of sp3. We are doing very large-scale simulations of amorphous silicon, which is a prototypical glassy amorphous structure. We've been searching for boron structures. Boron is one of those elements for which there are no old empirical interatomic potentials, just none. Its chemistry is so difficult. Same with phosphorus. We've done simulations of iron mechanics where here's a little dislocation. Is what happens when you shear a piece of metal, and people want to know how the atoms transform and slide past one another with quantum mechanical accuracy. And there are applications to more complex materials as well. I want to tell you in more detail about two of these because they let me talk a little bit about the learning process and what the challenges are. And so one of them is we set ourselves the silicon challenge is transferability and extrapolation is the big problem, right? The early days, especially in this field, people were very proud when they could get a scatter plot where every point lies on a line. And that looks very impressive if you are not used to seeing plots like that from machine learning because everything is near the training set and of course it works. But the model can still be useless. So what we want to do here is make a potential that works everywhere. So this is the extrapolation error should be somehow bounded, reasonable, and that's a domain-specific thing. It needs to be small enough that the crazy things don't happen. And silicon is a good example because it has a huge variety of crystalline structures, lots and lots of interesting defects, and because it's been studied so well using quantum mechanics, we actually know what the relevant defects are and the relevant structures. And this is my least favorite slide. It's the database that we've hand-built over 10 years to achieve make a good silicon potential. But this is no way to proceed. That's the challenge in some sense. So yes, we have a potential that does well, but its database has been hand-built with lots of domain knowledge of what's relevant, and even if I told otherwise, you would know that the way these highly specialized configurations of different defects came about because the potential wasn't very good there. And so I said, oh yeah, oh my God, that needs to be in the database. Okay, so of course it happened that way, it had to, but this is not possible really for every material in the future. So that's the challenge. But the potential when you do it, and we weren't sure whether this would ever stop, actually, could we actually build a potential that really does well? And it turns out we can. So this is the little example that I had before. These are all the other models on the market, and this red one is the SOAP-based, kernel ridge regression-based model, and again, errors with respect to the quantum target. So order of few percent, and that's great for doing materials. It works even for situations which are nowhere near the training set. So here are all the things we thought of in that big table. These are surfaces, I'll show the pictures in a minute. These are configurations which we didn't plan for and deliberately stopped before, rather than adding them, and we still get on the order of 10% error formation energy for these defects. These are planar defects, grain boundaries, and all the other methods, again, bring their very high errors. A very, very stringent test for such potentials is random search. So you take what this is, you take 8 atoms of silicon in random places in the box, and you just go down. You do gradient descent and see where you end up. And what you see here is that process done, and then energy and volume plotted at the end, with all the different models, including quantum and the machine learned model. And let me just do the convex hulls so you can actually see what's going on. And what you see is that the convex hull of the quantum search is this, the convex hull of the machine learned potential search is this, and everything else is complete garbage. So the empirical potentials, although they can be made to do diamond-type silicon really well down here, their potential energy surface is essentially complete garbage up here for high energy and high volume configurations. Whereas the machine learned model, which was not trained with any of these configurations, the database is only low energy stuff, really does quite well. Here's a task that we love to do for every kind of material, and this is the sort of thing we want to do on a large scale. Phase diagrams. Here's diamond type silicon, here's liquid, here are the different high pressure phases. Quantum mechanics can be used to compute these at low temperature, 0 temperature, and these are transitions from one phase to another. You can do quantum mechanics at high temperature with molecular dynamics, but that's really, really expensive. Okay, so that point there is many months on a supercomputer. And that's not an independent point. That's just showing we can get a gradient as well. Whereas doing this model is, a week on a small cluster in my group. Okay, so and the reason they don't agree now with experiment is because the potential is fitted to a certain level of quantum mechanics, and we're claiming that this is the phase diagram of density functional theory, and it's not the same as experiment. And now people who develop approximations of quantum mechanics can look at that and assess how the different quantum mechanics approximations do. So I mentioned these properties that are extrapolated, that are not near the training set. Here they are. So this is a planar defect. Here's the bulk silicon structures, and I'm shifting the half of the unit cell. And what we've done here is error prediction. So there is an equivalent Gaussian process equivalent to the kernel ridge regression, and we can take that variance of the Gaussian process and think about that as a predictive error. And I've colored the atoms using that predicted error. And so what you see is that the model has these 10% errors, and it knows that these atoms are out of scope. So that's great. And lots of groups are using that to do active learning, building up new databases, and that's a good thing to do. Let me skip this. We are now doing sort of 100,000 atom simulations. We're finding crystallization. That's something to be seen shortly. I promised 2 stories. That was one. Here's the second one. So this story is on fluid methane. So that's a molecular system. It dominates a condensed phase, but molecular. It's dominated by weak dispersion interactions, bunch of methanes floating around. And the question was, are two-body interactions between pairs of methanes enough, or do we need many-body effects? And what level of quantum mechanics is required at all to figure out the equation of state, so the temperature, pressure, density relationship? And so this is now far beyond DFT. DFT is certainly known not to be good enough for any of these. So here's what happens when you take 2 methane molecules here. That's the axis of all of these panels. And you just move them closer and further away from one another. So the black lines are the highest level of quantum chemistry that we can essentially afford, coupled cluster theory. The red line I'll return to in a moment. And what you can do is try and fit this potential energy surface of 2 methanes using various ways. So an empirical fit using Lennard-Jones terms is this red line, and what I'm showing here are the errors. So look at the numbers here. This is 20 millieVs, 40 millieVs, and these are the errors in millieV of an empirical model. Pretty good at large distances, but quite atrocious up to 10 millieVs, basically half the value when you come close. We can reduce that using machine learning technology. Take the things that I discussed already. We call it a 6D dimer gap. This is a 6-dimensional model of this dimer, and we can reduce those errors by orders of magnitude, and these were the symmetric orientations that you have here. If you pick random orientations, more representative of the fluid, then you can see that the empirical model is still terrible, and the machine learned model really reduces all the errors to 10 to the minus 3. So we have nailed the interaction of 2 methanes. But what we're really interested in is the condensed phase. So other empirical models are available. This one is this one, but there are worse ones and better ones. Right? You can tweak the empirical models and adjust this error, the average error. This shows the average error on this dimer data set. But what happens to the density? So here's a particular state point, certain temperature, and we want the density, and that's the real answer. Okay, look at the gray points. So these gray points correspond to these empirical models, and it's very, very disturbing because these really, really bad ones that are really bad on the dimer, they're essentially nailing the density. And this one that's really, really good on the dimer is really bad. It has 10% error in the density of methane. Of course, you won't be surprised to learn that the empirical parameters in these bad models have been tuned to reproduce the density of methane at the expense of actually getting the potential energy right. So this is the right answer here for the wrong reason. It's not because you have the potential energy. What's even worse is that if we take our machine learned model, which now this is an expanded plot, which has an even smaller error on the dimer, like really, really tiny, it's terrible on the density. It's again 10% wrong. The right answer doesn't give you the right result. So what that shows is that this really is not a two-body problem. So you can nail the pair interaction of methane, sum that over each pair, and that really doesn't give you enough on the density. So what we've done is a series of many-body models, which I'll explain in the next slide. And there, again, this now is blown up here, you can see a correlation. So the better they do on the dimer, the better you do on the density, approaching, hopefully, by the end, the real answer for that state point. So this is what we had to do. So there's medium range physics in here. So there is van der Waals, interaction between the methanes, and the pair models take that into account. We know its functional form, it's 1 over r to the 6, but there's a hierarchy of models that you can do. So what we call TS star is Tkachenko-Scheffler, pair potential, it's basically 1 over r to the 6 on each carbon with a coefficient that is fixed. Then one can do a TS correction, a TS model, which is on-the-fly computed coefficient. So instead of a fixed 1 over r to the 6, for each configuration you compute a new one that you need to do a DFT calculation for that. So no long rate, no large scale MD. Or you can do the same but with a many-body dispersion model, again by Alex Tkachenko, which is not a pair potential of 1 over r to the 6. It's a many-body model, also needs a DFT computed coefficient, but it's very expensive. So what we thought we'd do is we take the TS star, which is really long range, and basically say that, look, whatever's beyond the fixed coefficient TS star, which is very, very cheap, is probably shorter range. Well, the real TS just has a different coefficient, so it's still long range but much smaller. The correction is smaller, and the MBD is very complicated here, but it goes, it's again, the correction, MBD minus TS star, is probably very small. And that we've tested that for a few configurations, and it's true. So our model is basically this. Take all the monomers of each methane separately, take the TS star long-range model, the 1 over r to the 6, and then fit the rest using SOAP and gap, using a short-range DFT, and then the many-body dispersion of Alex minus the Tkachenko, minus the fixed baseline, and fit that with 2 different models. And here are the customary scatter plots that we managed to do those fits. And here are the results for the density. So what you find is that once you do this at the right level of quantum mechanics, so that's hybrid DFT for the short range and many-body dispersion, you get these pink lines. And so it's a significant improvement. We only get 5% error now, not 10%. And the last 5% error is quantum nuclear effects. So that's something that I haven't mentioned at all. Hydrogens and light atoms aren't actually really following Newton's law. They are a little bit quantum mechanical, and people have worked out how to do a simulation that takes that into account once you have a fast potential energy surface. And again, Michele and others have been at the forefront of making software to do that. So we plug our potential model into that quantum nuclear simulation, and we are right on top of the experiment for the right reasons this time, because these potential energies are actually the right energies. And we can switch state point, go to a different temperature, and still reasonably, apart from the very, very critical point where there's a second order phase transition, really get very, very close to the experiment for the right reason. Okay, so I won't talk about other people's work very much, just to say that to support my claim that the problem is solved, there are many successes in molecules as well. I've talked about solids and condensed phases. This is a picture that I asked Anatol, and it was very kindly sent to me. This is the QM9 data set, a whole bunch of different ways of fitting the QM9, 134,000 molecules, and by the time you get to 10,000, many, many models get better than this benchmark line. But it's quite an arbitrary benchmark. There's no saturation either. So that's why I claim that we know how to fit for these small molecules, we know how to fit quantum mechanics. This is Alex Tkachenko's kernel ridge regression model on interatomic distances. Again, pretty good learning curves. And these errors of 0.1 EV per kcal per mole is excellent. It's like down here, basically, for these selected molecules. So each molecule is benzene, uracil, naphthalene, and so on, and he makes a separate model for each of those. It's a custom force field, and you nail it. Here's ANI-CC, which is 2 and 3 body descriptors like York-Baylor's, 3-layer neural network, and this is a model for arbitrary molecules, and these are torsional curves. So when you rotate the long chain molecule around one of its bonds, and this is really the final answer. This is their model, and these are other quantum models, and these are the empirical force fields, right? So force fields are really bad, and they're approaching really what the best quantum mechanics. So I just have 2 conclusion slides. If you believe my claim that we have now short-range quantum mechanical fitting tool, we can sort of stop some of us can stop doing machine learning and go back to doing physics and matrix modeling. So what are there are lots and lots of tasks. So we should include magnetism, explicit spin interactions, fit those spin interactions with our local, I put it as a black box, but it's a gray box. We know what's in it. Electronic entropy at high temperature, again, it's a local property. We can try and fit parameters of long-range electrostatics, and I put this slightly lighter. How to do that really well, we don't know. So that's a real outstanding challenge. If you want to deal with charge transfer, spin transitions of different molecules where the potential energy isn't actually smooth, it has cusps, those are quite thorny, but physics challenges. And then in the green boxes, I put a more sort of software engineering or more engineering application, not software engineering, but model engineering tasks. Yes, we need to do active learning, how to make the databases smaller and more general, how we can accelerate DFT&D. I'm sure this will be done, but it has been done for VASP already. But other codes will just take existing quantum codes and put these short-range QM fitting tools as standard into those codes and speed them up for any new simulation that you start. And then we can make more generic models and discover structures and phase diagrams. One of the outstanding challenges, but it's sort of a user challenge, is to make a universal organic force field, like Annie is, but better. And I think someone will do that in the next 5 years. I don't know who, and I'm sure there'll be competition to do that. But of course, that would lead to great new science. And sort of my last slide is really about the mathematical challenges that I'm quite interested in. So how do we characterize the relationship between fitting databases and the accuracy of very, very complex predictions, so complex properties like equations of state and so on. How do we give global accuracy guarantees? So for these specific systems, I don't want to have holes like MTP does. And that's driving me towards regularized polynomial models and similar. And there's another way to look at all of this. There's an inverse problem here. Suppose I want a given property, like here's a crack, and I want to make sure that my model is good enough. What do I need to put into the database in order to get a certain property right, even if I don't achieve global guarantees? And that's what we do in practice by hand. How to do that a little bit more automatically is, I think, a really important question. Thanks very much for your attention, and happy to answer questions.